All right, so I've done my best to set up here. It's not the most appropriate location, but as far as I've checked, quality seems to be reasonable. So I'm going to start taping, and I'll probably cut every 20 minutes or half an hour or something like that, because the uploading into YouTube sometimes is an issue if the file gets too long. Anyway, as I mentioned in the email or in Blackboard, we might be at this for a little while, or maybe to the whole thing. So we have to see how the format works, and then we'll communicate and try to optimize it best we can. So here we go. Let's take a look at the use of the computational deflections using virtual work that we've been looking for in the last few classes. We've already done a number of examples, and I'm just going to look at one more today to emphasize the possibility of using different coordinates to describe the stress resultants of moment, shear, and axial force, the advantages that may come, so that you can make up your mind as to which way you'd like to go when you set up the coordinates. In addition to that, we will add to today the computation of deformations when the action that's producing them is not loads but temperature. So I start with this structure. Okay? We're going to take it to have 2h, and in order to have something where we're not always having 45 degrees, let's say this is h. This point is A, B, and C, and the loading, it's a uniform load W acting on bar BC. We say that our elements have E, I, AV for shear, and A for area, and G for shear modulus, and that applies to both bars. By the way, yeah, I think I didn't mention when I was introducing the topic, I'm going to account in this case for all the effects, not just bending. Okay? We've seen that when we were doing a beam, bending was really sufficient because the only other contributor, which was shear, was very small, and so we can neglect it. That's not to say that we don't need to know how to do it. So in frames, bending like this, kind of a curved beam, bending is still overwhelming the largest contributor. But axial force sometimes starts to play a sufficiently large role to be considered, sufficiently significant role to be considered. And in this example, I'm going to include all of them. Okay? So the properties of the bars are the same. The modulus of elasticity is E, the shear modulus is G, the moment of inertia is I, the shear for shear purposes area, the area for shear purposes is AV, and the area for axial effects is the actual area A. And our question is to calculate delta C in the vertical direction. Okay? One of the things that is an issue with this board is, for reasons unknown to me, it doesn't erase well. I tried an eraser, it doesn't work very well, it makes a whole mess. With a towel it's a little bit better, but it's still a mess. So once it gets filled up, which will have to happen, we'll have to, I can't pause the video, but we'll have to undergo, and I'll have to clean it up before we start the next round. So anyway, we have that, and if our objective is to calculate the deformation at C in the vertical direction, the first thing we would do is to take our structure and apply a unit load at the C location in the direction of the question. Had the question been what is the deflection at C in the horizontal direction, then the 1 kip load would have been applied in the horizontal direction. Okay, from this diagram, we have to get M1, we have to get V1, and we have to get N1, which are expressions of the moment, shear, and axial force throughout the structure. That is, we need a mathematical description of what is the moment anywhere, what is the shear anywhere, and what is the axial force anywhere. Since anywhere is anywhere in the structure, what we need is a way to describe what are the positions along the structure, and that's what we refer to as the selection of coordinates. We also have, of course, the P-sketch, which is this if you'd like could be called the one sketch. And then we have the P-sketch, which is the effect that is producing the deformation, which is this sketch here. Now, I am going to just draw it in small here on this side. W, and this is the P-sketch, and from this sketch we're going to find MP, VP, and NP everywhere. We must use the same sign convention in both, and we must use the same coordinates in both, because we are going to then say that the deformation at C in the vertical direction is the integral of M1 times the strains due to the P, which for loading becomes NP over EI, ds, right? And that's the effect of bending. And when we put tau here, we mean over the complete structure, plus the integral of V1 times the strain due to the shears, which is Vp over AVG ds over the complete structure. That's the effect of the shear, or the contribution of the shear to the deformation, plus the integral of N1 times NP over AE times ds, and that's the contribution of the axial, right? So what we need in essence are these sets to place them up here and perform the integration. Our ability to compute M1, V1, N1, MP, VP, and NP is related to our ability to understand how to perform, how to draw a correct free body diagram, and of course how to do statics. So because this board is not very large, I'm going to have to use some sort of strategy to try to at least not have to be erasing every 2 seconds. So I'm going to assume, or not assume, I'm going to ask you to remember, when I'm talking, I know it, that these two horizontal dimensions are 2h, this vertical dimension is h. So I am going to erase this part here and work on this left side of the board to try to do some calculations. Okay? So let's see how this erases the best I can. As you can see, it makes a smudge, it's a mess. But I got this. Okay. So that we have a little space to work, more or less clean. So let's start with our right side. Let's start with our unit diagram, right? So I'm going to state that the coordinate x starts from that end and runs to the left. With that coordinate, I'm going to take this bubble as a free body diagram. And from that bubble, let's see, I start here on the left, extreme left. So I have that, I see the one kip. Now I have to decide on sign convention. At this point I haven't done anything, so I can choose whatever I want. I'm going to choose going up here to be plus and call that V1. I'm going to choose going to the right plus, and that's N1. And I'm going to choose counterclockwise on this side as plus, and that's M1. And this distance from here to here is clearly X, right? Because that's the size of that free body. This is the beginning of X, that's the end of that cut. From that free body diagram, we can say, if this point here is O, that from some of the forces in the X direction equal to 0, to the right being positive, we conclude that N1 is 0. From the sum of the forces in the Y direction equal to 0, with up as plus, we conclude that V1 is equal to 1. And from the sum of the moments about O equal to 0, taking clockwise as positive, we conclude that minus M1 plus 1 times X is equal to 0. Therefore, M1 is equal to X. So we have succeeded computing on bar BC, right? That was A, B, C. So we've succeeded computing on bar BC the moment M1, V1, and N1. Now we can do bar AB. When it comes to bar AB, in bar BC, it's kind of obvious what the coordinate is. On bar AB, with a little experience, it's also obvious. But at the beginning, when you're just being introduced to this thing, it might not be obvious to you which one is the easiest thing to do. So I would think that it would be probably the most intuitive, I don't know, to say, okay, if I have to deal with AB, I'm going to calculate the reactions at A, and then I'm going to take a bubble from A upward, okay? So, in order to save a little bit of time, not time, but space also, I think it's obvious that if I take a free body diagram of the complete structure here, right, that this reaction in the vertical direction is one kip from some of the forces in Y, that this reaction is equal to 0 from some of the forces in X, and that the moment at this end, summing moments, is this way, and it's equal to 1 times 4H, right? So those are the reactions at A. Then, with those reactions, I can without any problem, right, take this bubble and use a coordinate that begins here and it's moving parallel to the bar and call it Z, right? So that bubble then looks like this. Over here there is a 1, there is a 0, and there is a moment of 4H. Over here, I still am free to choose any convention that I want, because once I'm in a particular bar, I can choose any connection, any notation that I like, as long as I remain consistent from one drawing to the next. So here, I will choose. Let's see. Let me do it the way that I did it in the notes here, so that I don't switch around. Okay, I took this to be N1, so inward. This to be V1, and the moment M1, I took it like that, clockwise. Now, another thing that is helpful for visualization purposes is probably not to draw this one below, but to draw it like this, because the two components then become much more obvious, that this one is like this and this one is like that, right? And this is the one. So this bar inclination is 1 in height, 1 in the vertical, 2 in the horizontal. So its length is square root of 5h, right? And you can, from elementary trig, convince yourself that this component is 2 over square root of 5, and this component is 1 over square root of 5 of that load. So we have this reaction of 1 going into 1 square root of 5 and 2 square root of 5. And then we have a moment of 4h, no horizontal, and we have shear, axial, and moment. From sum of the forces in the x direction equal to 0. Now here this bar is inclined, so I would normally do this in my presentations. I would say, okay, this is x and this is y as far as this drawing is concerned. So if I say sum of the forces in x, I really mean this way, right? Taking, let's say, that way as positive along the positive x. So I would have 1 over square root of 5 minus n1 is equal to 0. Therefore, n1 is equal to 1 over square root of 5. Sum of the forces in the y direction is equal to 0. Going up, or that way, is plus, gives me 2 over square root of 5 minus v1 is equal to 0, from where v1 is equal to 2 over square root of 5. And from sum of the moments about O equal to 0, this goes right through, so we get sum of the moments about O equal to 0, taking clockwise positive, I get 2 over square root of 5 multiplied times z. I should have noted here in this sketch that from here to here is z, right? And so 2 over square root of 5 times z minus 4h, which is counter, plus m1 is equal to 0. And therefore m1 is 4h minus z, 2 square root of 5 times z, right? And so we have, let me see, double check myself here, 4h minus 2 square root of 5z, okay? So we have completed the one sketch, all right? We're done with this sketch. We have m1, v1, and n1 in both bars. So in order to transcribe it and keep it handy, I have to put it somewhere that it doesn't occupy the whole board as this one is doing. So for that, let me think. The best way to do that right now is going to be, yeah. So this is what I'm going to do. Let me erase this. Draw this one again, if necessary. Okay. Sorry about that. So let's let's transplant the results that we just obtained to there. So we can say on bar 1 we have M1 is equal to X, V1 is equal to 1, and N1 is equal to 0, I believe, right? Yes. And then on this bar we had M1 is equal to 4H minus 2 square root of, this is X starting here. So here we have M1 equals 4H minus 2 over square root of 5 Z. We have V1 equals to 2 over square root of 5. And we have N1 equals 1 over square root of 5. Okay? X starts from here and it goes up to 2H. C starts from here and it goes from 0 to square root of 5H, right? That's it. Now we need to do exactly the same thing using the loading condition. So I have to erase this stuff best I can. Clean it up a little bit. Okay, and now we do the P-loading. So for the P-loading, let's see, I'm going to put here the structure where we're going to transfer the information. The load is here. Our first free body diagram is just like before. We don't need to make decisions regarding sign convention or free body diagrams or coordinates, because we made all those decisions on the one load. So taking this free body diagram, we find this with the load W. This distance is X. This load is WX. Here we have an axial, we have a shear, and we have a moment. In this case, this is the moment MP, the shear VP, the axial MP, and that's our load WX, which is the resultant of that at a distance of X over 2 from that point. That is complete, and therefore we use our statics and we say sum of the forces in X equal to 0, from where we find that NP is equal to 0. Sum of the forces in Y equal to 0, from where we find that VP is equal to WX. Sum of the moments about O equal to 0, which is here O, equal to 0, taking clockwise as plus, I get minus MP plus WX times X over 2 equal to 0, from where MP is equal to WX squared divided by 2. Okay? So that concludes everything regarding bar AB. We have NP, VP, and NP. Now we need to do bar AB. If I continue, just like I said before, the first thing would be a free body diagram of this complete structure. In other words, a bubble like this. In this case, the resultant here is 2WH. From sum of the forces in Y, oops, doing the same thing again. From sum of the forces in Y, we find well actually it's okay, I'm not going to do it there, that this reaction is 2WH. We find that the horizontal reaction is 0, and we find that there is a moment here, and that moment is obviously this distance, this load times this distance, and that distance is 1h here plus 2 h's is 3 h's, so this is 6WH squared. So those are the reactions, right? I can't stop too long with the calculation of the reaction because that's just too elementary, right? That's just as elementary as it gets. So free body diagram with a complete body, some of the forces in Y, some of the forces in X, some of the moments about here, that's it. Now we need to do what? We need to do the same thing, take the free body diagram. We have a coordinate here that begins that way and that it's called Z, and so our bubble goes like this, and that's valid anywhere along the bar AB. That free body looks like this. Over here is the load, there is no horizontal, and there is this moment. This load has a component like that and a component like that. The vertical component is 2 over square root of 5. When I say vertical, I mean the shear. 2 square root of 5 times 2WH. This one is 1 over square root of 5 times 2WH, right? Over here, we have our shear, our axial, and our moment, and we have no choice but to use the same directions as before. And before, I believe we called this the shear, this the axial, and I want to say that we used a clockwise moment to be positive, so this would be VP, NP, and MP. I'm going to double check myself, make sure I didn't change any sign convention. Yes, that's correct. Okay, so now we do our statics, and again our X and Y are now inclined, and so we say from sum of the forces in the X direction equal to 0, we have that NP is equal to that one, which is 2WH over the square root of 5, right? From sum of the forces in the Y direction equal to 0, in the inclined Y, we find that this VP is equal to 4WH over square root of 5, and from sum of the moments about O equal to 0, taking clockwise to be positive, we find 4 over square root of 5 multiplied times WH multiplied by Z. I got too crowded here, but remember the distance from here to here is Z. So 4 over square root of 5 WH times Z is positive. Nothing else, right? So plus NP, plus NP, and then this moment here, which was 6WH squared, right? Plus NP minus 6WH squared is equal to 0. And from there, we find that the moment MP is equal to 6WH squared. That went to that side, minus 4 over square root of 5 times W times H times Z. Okay? So we've completed the statics on the second sketch, and we can now transcribe the results. So I will do that by erasing this. And showing that on this bar, MP, we had MP equals WX squared over 2. We had VP equals WX, and we had NP equals 0, with X starting this way. Over this bar we had MP equals this thing, 6WH squared minus 4 over square root of 5 WHZ. We had VP equals 4WH over square root of 5. And we had NP somewhere, 2 WH over square root of 5. Okay? Now I will erase this side. And we say, okay, look, at this point we have finished doing everything that required knowing statics, right? Now all we need to do is to show that we know how to express, how to plug in those things into the equation, which essentially means knowing what are the limits of the integrals. Because after that, you can just give it to anybody that doesn't have the slightest clue about structural analysis and just say, do these integrals, and they can obviously do it if they know a little calculus. So we then say here, delta C in the vertical direction is equal to the integral of M1 MP, the integral of N1 NP, and so on, right? So let's begin with bending. Could organize it per bar or per bending. Let me do it first bending, then axial, then shear. So for bending, this bar M1, MP, W x squared over 2 EI dx, and the limits are from 0 to 2h. That took care of that bar. Plus the integral. We have to do this bar bending now. M1, 4h minus 2 over square root of 5 z, that's M1. MP is 6 WH squared minus 4 over square root of 5 WHZ, close parentheses, dz over EI. Excuse me, there is a call here. Let me see what it is. Yes, I'm teaching now, I'm taping. Bye. Sorry about that. Okay, so what? So we have the expression, right? And the limits of this integral are, where does z go? Z starts at 0 and goes how far? This is 2h and this is h, so it goes up to square root of 5 H. And that is bending. That's how much the deflection at C in the vertical direction is due to bending. Plus, let's see how much is the direct deflection at C due to shear. So we have here the shear is V1. So the first bar we have 1 times. The shear here is WX, and we have to divide it by AVG. That's the strain in shear. And then we have to multiply times ds, which in this case is dx. And the integral goes from 0 to 2h. So we got the shear contribution here. Plus, the shear contribution here is the integral. Again, like before, from 0 to the square root of 5h of V1, which is 2 over square root of 5, times Vp, which is 4WH over square root of 5, and that is dz divided by AVG, right? Of course, AVG could be different in each bar, right? But in this case, I said it is the same. So that's what we get. And this is the contribution of shear. Now we need the contribution of axial plus, what is the contribution of axial? The axial here times the axial here is 0 for the first bar, plus the axial here is 1 over square root of 5. The axial here divided by AE, which is 2WH over square root of 5. AE is the strain due to the load, and that is times dz, and the integral goes from 0 to square root of 5h. Okay? And this is axial. Okay? Let me see. All right. I am going to have to erase and so on to show something, but let me just cap it by saying at this point I'm not going to do the integrals in detail because they're a little too tedious, and as far as I can see they don't show anything. I assume that nobody here that has any problem on doing these integrals, right? I mean, it's just a polynomial, you multiply, you do the integration. So we would have this to be the contribution of bending, this to be the contribution of shear, this to be the contribution of axial. If we actually had numbers for W and H and A and E and I, and we computed an actual value, what we would expect to get is that of this deflection, which comes from the addition of this, plus axial, bending, shear and axial, the bending would probably be 98%. Maybe the shear would be, you know, 0.5%, and maybe the axial would be 1% or something like that. So overwhelmingly, the contribution to the deformation on structures of this shape, this form, which are long and bend a lot, comes from the bending strains. And in practice, most of the time we don't bother including the contribution for shear or the contribution for axial. But as I said, it's necessary to know how to calculate them because there are instances in which it's absolutely necessary to include them for reasons that will become apparent later on in the class. Okay, so let me see if I can think of any questions here that might pop up. I don't see anything. Again, if you are clear on your statics, then this is a piece of cake. If you are not clear on your statics, then this is a nightmare. Okay? So it's a better idea to be clear on the statics. It's really very easy. Take a bubble and be disciplined, right? Okay, so I think I will leave the contribution of bending, not erase it, and then I'm going to redo the problem using a different coordinate set for the second bar to illustrate that in this case you would actually be able to save some time if you had made that choice. But because the file now, it's probably 35 minutes or so at least, I'm going to stop and start again so the file sizes are not too large.